Okay, welcome back to week 3 of your online learning. I hope everyone's doing okay out there, staying safe, staying healthy. Um, so this is actually going to be the last couple lessons that we're doing with optimization. After these next few days, we're going to be done with 3.7 and we're going to actually move on to chapter 4, which will be obviously a brand new chapter for us. So in these last couple days of optimization, we're going to be talking about cost. Um, so last week we talked about optimizing areas of rectangles, optimizing volumes of boxes, things like that. This is going to be more about how to determine the most efficient cost of square and rectangular shapes. So this obviously has a lot of real world implications. Let's just say, for example, you're building a fence around your yard, right? You don't want to overpay for this fence. You want to find the optimal cost that allow you to build this fence for the least amount of money. Okay, and actually that's going to lead us into our first example here. What this first video will just be example 1. The second video that I post will be example 2, and then your practice problems today will obviously be very similar to the video examples. Okay, so I posted this example, this PDF, on your Google Classroom, so you can print this off if you want to take notes on it. If you'd rather just pause the video and rewrite the problem in your notes, you can do that. But you're going to need to have this problem in front of you because we're going to be doing some highlighting and underlining and annotating here. It says Jane wishes to enclose her proposed 1944 square foot swimming pool area with a fence. Okay, so she's got this swimming pool that has a certain area and she wants to put a fence around it. The area is going to be a rectangular shape. Okay, so just like last week we talked about how a lot of times on these problems we just want to visualize kind of this scenario here. Okay, so I'm going to draw a little rectangle here. Let's say this is our X, this is our Y. So the area is rectangular shape, we got that taken care of. 3 sides will be enclosed with a chain link fence at $4 per foot. Okay, and then it goes on to say one side will be a privacy fence with redwood fencing at $8 per foot. Okay, so it looks like it doesn't tell us which sides are enclosed, it just tells us 3 of the sides. So let's say we have chain link fencing around this side of the pool, this side of the pool, this side of the pool, and I don't know, let's just say this side faces the road, so this is where she wants her decorative fencing. Okay, so I'll make that maybe a different color or something, or different weight. So let's say that's the decorative redwood fencing, and obviously one fence is going to cost a little more than the other. So it says find the dimensions of the rectangle so that the cost of the materials is minimized. Okay, that's a key word that we talked about last week. Whenever you have maximized or minimized, that is your optimization equation. Okay, so our steps, at least to start, are going to be really similar to last week. I'm going to have a constraint equation. Okay, and we have to look back at the problem and say, what are we being constrained by? Okay, it says Jane wishes to enclose her 1,944 square foot swimming pool area. Okay, so this is the area of the swimming pool. We can't make it any larger, any smaller than that. She's already built the swimming pool. This is the area of the swimming pool. That's our constraint. Okay, so we're constrained by the area of the pool that was already built. Okay, and that equation, just like we said last week a bunch of times, x times y, and I'm going to set that equal to 1944. Okay, so we have our constraint equation. We need to find our optimization equation. If we go back to that last sentence, it says find the dimensions of the rectangle so that the cost of the materials is minimized. Okay, so it looks like we're trying to optimize our cost, right? We want to find the critical point where cost is at a minimum value. Okay, all right, so here's the extra piece that we're going to have to do this week. When you're looking at cost, you always have to ask yourself, what is cost related to? Is it related to perimeter? Is it related to area? Is it related to volume? What are you paying for? Okay, so let's go back in the problem where it gives us our dollar amounts here. It says will be enclosed with chain link fence at $4 per foot And then the privacy fence will be $8 per foot. Okay, so it looks like you're paying for this fence by the foot. Okay, and when you're paying by the foot, that's the fence that you're putting around the swimming pool. So you're building a perimeter by foot around this swimming pool. So cost is related to perimeter. Okay? Okay, so now that we know cost is related to perimeter, we need to set up our perimeter equation. Okay, so this is going to be an x, this is going to be a y. And we can say that it costs us $4 per foot of all the chain link areas. Okay, so I'm going to say two x's and a y, right? X, x, y. Plus I also have to pay for the decorative fencing, which is this piece right here. Okay, and when I add all this together, $4 for those three sides, $8 for this one side, that's going to give you my cost. Okay, so I'll put my C for cost. Okay, before I do anything else, let's distribute and simplify this. So this is going to be 8x plus 4y plus 8y equals your cost. Let's just combine our y's right now. Plus 12y equals your cost. And now we're back to where we were last week, where we talked about how we have two different variables in this equation, but we have another equation here that we can rewrite, so that way we only have one variable in this equation. So let's say y is equal to 1944 over x. Okay, so let's make it all in terms of x here. So we can solve what our x dimension is. This is going to be 12 parentheses, and I'm going to write 1944, and I'm just going to make over x, I'm just going to change that x to the -1. We all know that's going to help us when we start taking derivatives, and that's going to be equal to my cost. Okay? All right, so we have our cost equation set up. This is going to help us obviously find what our x dimension is. Okay? In order to do that, we need to find our critical points. And then we need to figure out, is that critical point a minimum or a maximum? So to find your critical points, again, just like we did all last week, we want to take derivatives. So the derivative of this equation would be 8 minus, okay, I'm going to have to multiply these two together and then bring the -1 out front. That would be 328 x to the -2nd, and then when I take the derivative of this constant, it becomes 0. Okay, so what I did here, I kind of skipped a step. I did this times this, okay, and then when I take the derivative of that, I bring this -1 out front, and it gets me to here. Okay, all right, so let me just rewrite this. It might be a little bit easier to solve for x if I place that in the denominator, just so I'm able to move things around maybe a little bit easier. X squared equals 0. Okay, so I'm going to take this 8, bring it over to the other side. So I'm going to have -328 over x squared. Losing you guys here, I'm going to slide this up. Equals -8. Okay, so I'm going to multiply both sides by x squared. Okay, and then I'm going to have to divide out this -8 to the other side. So this is, when I do that, I'm going to get 2,916 equals x squared. When I take the square root of both sides, I get x equals 54. 54 feet. Okay, so that tells us, if I go back up to the swimming pool, that these dimensions of my axis should be 54 feet, 54 and 54. One thing that I haven't done yet, I just want to check and make sure that this critical point actually is a minimum, right? We don't want this to be a maximum cost. We want this to be a minimum cost. So in order to do that, we take the second derivative, okay? So if this was my first derivative right here, okay? Let's take our second derivative. I'm running out of space here, but I'm going to say my second derivative would be, let's see, the 8 would go away. That would become 0. the negative 2 would come out front and be multiplied by 23,328. Negative and a negative would give me a positive. So it would end up becoming 46,656 x to the negative third, which is also 46,656 x to the third. Now, if I take 54 and plug it in right here, this divided by this is still going to give me a positive number, which means that I'm concave up, which means our critical point is right here. That's great. It is a minimum. Okay, so we did find the spot where our cost is minimized for our x value. So x would have to be 54. In order to find what y is, again, like we've done on all these problems in the past, all I need to do is this one last step. Divide 1944 by 54. And let's see, I didn't do that. I'm going to have to do that in my calculator. 1944 divided by 54 is equal to 36. Okay? So there's your dimensions of your perimeter for your fencing. Okay? Go to example 2, and I'll do one more of these with you.